All right, in this video, we're going to take some notes that introduce three intermolecular forces. And we're going to do that with this piece of paper, which has been cut into thirds, starting with the weakest of the intermolecular forces first and working our way up to stronger intermolecular forces. The first intermolecular force we're going to learn about are called London dispersion forces. And London dispersion forces are sometimes called van der Waals forces, but the word van der Waals forces is also used to describe all intermolecular forces in general. So we're going to use this term London forces or London dispersion forces. We'll talk about those in a moment, but let's just preview all three at once first. The second intermediate strength of intermolecular force we're going to learn about are called dipole-dipole interactions. And we'll learn in a moment that these are due to permanent dipoles, whereas London dispersion forces are due to temporary dipoles. Last but not least, we're going to talk about an intermolecular force which has been named really poorly by chemists. It's referred to as hydrogen bonding. And you've probably heard of hydrogen bonding before. However, it's important to note that technically this is not a chemical bond in the conventional sense of the word. It is an intermolecular force of attraction. It's not a covalent bond or an ionic bond or a metallic bond. It is an intermolecular force. And so the fact that it's called hydrogen bonding is a little bit misleading. Now, before we get into the details of all of these, I want to make a note that in this direction, we're talking about weaker forces. So I'm going to draw some arrows pointing this direction, and I'm going to draw some arrows pointing in this direction and write the word stronger, because as we go up the list vertically, we're going to be talking about stronger intermolecular forces of attraction. So we have our three intermolecular forces: hydrogen bonding, dipole-dipole interactions, and London dispersion forces. But we're going to start with the weakest first and talk about the mechanism by which these operate. So we'll zoom in here to the part of the foldable which introduces London dispersion forces. And we're going to draw a diagram inside this flap and leave enough room for two H2 molecules to be shown and plenty of room for an electron cloud around them. Now, before you draw the electron cloud, we're going to remember that this would be a molecule classified as nonpolar. In other words, we wouldn't expect the electron cloud to be lopsided. It wouldn't have a dipole moment. However, an electron cloud is dynamic, it's not static, and there are temporary fluctuations in this electron cloud. So let's imagine one that's happening. And again, I'm drawing an electron cloud that actually has some polarity to it, and that seems odd for a diatomic hydrogen. However, these instantaneous dipoles do exist. There are momentary fluctuations in that electron cloud. Now, a momentary fluctuation or an instantaneous dipole in this electron cloud will actually induce a temporary dipole in an adjacent molecule, in an adjacent nonpolar molecule. So I'm going to draw another H2 molecule, and notice how I'm carefully drawing the orientation of that electron cloud. This is the intermolecular force of attraction, and it is caused by these two instantaneous or temporary dipoles interacting with each other. So I'm going to write IMF here for intermolecular force of attraction, and then I am going to write on the other side here a few phrases about what's going on. The first note to make about London dispersion forces is that they are due to temporary, in other words, instantaneous dipoles. These are not permanent dipoles. Another very important note is that London dispersion forces act between all molecules. In other words, any molecules can exhibit this intermolecular force of attraction, even nonpolar molecules. And finally, we want to make a note that larger molecules, which have larger electron clouds, are more polarizable and therefore lead to stronger London dispersion forces. So I'm going to write that larger electron clouds are more polarizable, so lead to stronger LDFs. And LDFs is the abbreviation we're using for London dispersion forces. So we'll save some room on the back for some other notes later, but that is a summary of the first intermolecular force we want to look at. The second intermolecular force we're going to look at are dipole-dipole interactions. And again, we're going to draw a little diagram here, and we're going to write a few phrases. The diagram we're going to draw is of an interaction between two molecules of hydrogen iodide, also known as hydroiodic acid, and we're going to draw a Lewis diagram for that molecule. And of course, you know that this is a polar molecule, and I'm going to draw that lopsided electron cloud like this. And like we did before, I'm going to draw another molecule off to the side here, orienting it in this way to show an interaction between the positive end of one molecule, that's where the hydrogen is here, and the negative end of another molecule. And again, this is the intermolecular force of attraction we're studying right here. However, unlike the previous example, this is due to a permanent dipole. Hydroiodic acid, or HI, is a polar molecule. That's not a temporary dipole, that's a permanent dipole. There's always going to be more electron density on the iodine side, so we call that a permanent dipole. And when we talk about dipole-dipole interactions, we're talking about polar molecules. So unlike London dispersion forces, which can operate in any molecule, these only act between polar molecules. Molecules which have a permanent molecular dipole. Let's talk about the third and final intermolecular force, which is hydrogen bonding. Hydrogen bonding is a special case of a permanent dipole and really pertains to a bond dipole that exists when hydrogen is bonded to N, O, or F. In other words, if hydrogen is bonded to an extremely electronegative element, then we end up with a very, very strong bond dipole. A bond dipole that's so strong that it gets its very own classification. I'm going to draw, just like before, another molecule. And it's very similar to the previous example, only this time hydrogen is bonded to one of these three very electronegative elements. The three electronegative, or the three most electronegative elements which get this special consideration are N, O, and F. So, first, we want to make a note This is the intermolecular force of attraction we're studying, and it is a special case of an extra strong bond dipole. It only is exhibited, excuse me, that says a special case of an extra strong bond dipole. It's only exhibited when hydrogen bonded to N or F in one molecule is attracted to a lone pair on N or F in another molecule. That's a definition that really should be read a few times and thought about really carefully. This is probably one of the most commonly misunderstood concepts in introductory chemistry. So make sure you understand that this is not referring to hydrogen bonded covalently to something else. That is not the hydrogen bond. The hydrogen bond is an intermolecular force, one that operates between molecules, between one molecule and another. And it can only operate if the molecules in question have covalent bond between hydrogen and one of these highly electronegative elements. And that's what we call hydrogen bonding.